The design of a distillation column involves many numerical calculations, including tray and column sizing, heat transfer calculations, and material balance calculations. Here is an example of a design calculation for a distillation column. Problem statement. A distillation column is required to separate a feed stream containing 50 moles % N-hexane and 50 moles % N-heptane into two products: an overhead product containing 90 moles % N-hexane, and a bottoms product containing 90 moles % N-heptane. The feed rate is 100 kmol/h, and the reflux ratio is 2.5. The desired product purities are achieved by using a total of 20 trays in the column. Calculate the diameter and height of the column. Solution. 1. Determine the number of theoretical trays. The number of theoretical trays required for this separation can be calculated using the McCabe-Thiele method. 1. The method gives the number of trays as north equals lane R, lane XDYD, XDXW, plus 1, where R is the reflux ratio, XD and YD are the compositions of the distillate and the feed, respectively, and XW is the composition of the bottoms product. For this problem, R equals 2.5, XD equals 0.9, YD equals 0.5, and XW equals 0.9. Plugging in these values, we get north equals lane 2.5, lane 0.9 to 0.5, 0.9 to 0.9, plus 1 equals 9 trays. However, the actual number of trays required is 20, so the column will have 20 actual trays. 1. Determine the column height. The column height can be calculated using empirical correlations such as the Gilliland correlation or the O'Connell correlation. 1. For this problem, we will use the Gilliland correlation. H equals N, HTU, L, V. Where H is the column height, N is the number of actual trays, HTU is the height of a theoretical tray, L is the liquid flow rate, and V is the vapor flow rate. HTU can be estimated using the following correlation. HTU equals 1.35 HETP, where HETP is the height equivalent to a theoretical plate. For this problem, we will assume HETP equals 0.8 feet tray. The liquid flow rate can be estimated using the following equation. L equals F1 plus R, where F is the feed rate and R is the reflux ratio. The vapor flow rate can be estimated using the following equation. V equals L, R plus 1. Plugging in the values, we get L equals 100, 1 plus 2.5, equals 27.03 kmol, HV equals L, 2.5 plus 1, equals 135.13 kmol, HHTU equals 1.35, 0.8, equals 1.08 feet tray. H equals 20, 1.08, 27.03, 135.13, equals 4.33 feet. 1. Determine the column diameter. The column diameter can be estimated using empirical correlations such as the panhandle A or B method. 1. For this problem, we will use the panhandle A method. D equals V, 0.8 per V max, caret 0.5, where D is the column diameter, V is the vapor flow rate, ρ is the vapor density, and V max is the maximum allowable vapor velocity. The maximum allowable vapor velocity is typically around 1 meter per second. Plugging in the values, we get ρ equals 0.9 mn hexane plus 0.1 mn hept,